So, hi everyone, and welcome to this virtual conversation dedicated to multifunctional parts built with additive manufacturing. I'm Katie Lindsay, managing editor at 3D Additive Media, and have the honor to moderate this conversation between Elena and Alexander. So, before we dive into our conversation, I would like to highlight some of the main objectives we aim to achieve through this panel. Our speaker that are present here are going to help you understand the concept of multifunctional parts. We'll discuss the various manufacturing processes, the appropriate material solutions, as well as the right design steps that may enable you to obtain multifunctional parts. They will also share a few examples of use cases in vertical industries where multifunctional parts have been built with additive manufacturing. And of course, they are going to respond to your concerns regarding optimization of multifunctional parts. So I'm going now to give the floor to Elena so that she can introduce herself as well as the company she's working for. Elena, can you go ahead?
Yeah, thank you so much, Katie, for this nice introduction and obviously for the invitation today. So my name is Elena Lopez. I'm a chemical engineer from the background here, and I work at Fraunhofer IWS, so Institute for Material and Beam Technology in Dresden, Germany. Dresden is quite close to Prague, so it's in the east side of Germany, and Fraunhofer IWS is just one of 72 different Fraunhofer institutes devoted, let's say, to applied research in Germany, but also in Europe. So it's the biggest institution concerning applied research in Europe. So my role in the company is to lead the department for additive manufacturing, where we are more than 35 people dealing with actually all well-known technologies from metal up to polymers and multi-material approaches. And if you know Fraunhofer, you would know that we really work quite close to the needs from industry, even though we're trying also to keep pace with the latest scientific issues out there. So I think that's it from my side, and happy to be here today.
Thank you, Elena. What about you, Alexander? Tell us more about you.
Happy to. So I'm Alexander Pluk, CEO of Additively, background in optimization, and really our work and software whole purpose is how to exploit potential of multifunctional design, manufacturing, material properties. How do we look at the objectives and different competing objectives that we can resolve with multifunctional parts? And we've worked with a whole number of different brands and material systems, from ceramics within electronics industries, metals and aerospace, polymers and automotive, and so on. So there's lots of opportunity from different technologies that are both emerging in additive and traditional manufacturing processes. Really excited to be here today. Thank you, Katie.
Oh, it's a pleasure. I would like to remind our attendees, because I know they are still coming, that if they have any questions, please feel free to write your questions in the Q&A so that our speakers could read them after the main conversations and reply directly to you. So just to start, how would you define the concept of multifunctionality? Elena, do you have any point of view regarding how you would define this concept?
Yeah, so as the name itself says, we consider a part that is multifunction if we have definitely different functions included in this part. It could be electrical functionality, it could be a mechanical functionality, a thermal functionality, and so on, further and so on. And so for us, the concept is somehow wider related to these different functionalities than just, let's say, like in some cases is expected just only multi-material approaches and so on. So we see also the possibility to have one single material with different functionalities in additive manufacturing.
Correct. Alexander, is there any other definition that we can see?
I think,
regarding this.
Sure. So I think kind of multifunctional in itself is around a part that can serve multiple uses, right? And I think all in the world, and I think one of the challenges that we have as engineers more broadly is how do we get the things that we're producing to do as much as possible, right? And those functions can be physical, but they also can be business related, right? There's concepts such as lead time, such as cost, such as sustainability that also can come in and be tuned with the drivers that deliver multifunctionality. So I think, Elena, you're really right that we have single material systems that can have different functions. Composites come to mind with fiber orientations. We have systems coming out of metal-based approaches where you can discrete or gradient. I don't know, Elena, you're going to show something shortly around that. And I think most production techniques have variables that can drive and affect material properties. So I think that's a key concept here, material properties within multifunctionality. But I would say that without the ability to look at the objective you're trying to achieve, multifunctional for its own sake doesn't have value. So I think it's always good to pair that with what is the value that we're trying to achieve.
All right. I've heard that you've mentioned some of the challenges related to most production techniques, but what about additive manufacturing itself? What are the main challenges engineers might encounter when designing a multifunctional part for AM?
Well, I think if we zoom out and think kind of what are ways that we can deliver multifunctionality with an additive, and so really you're looking at the different production technologies that there are, right? And we've got kind of the more established production technologies, the laser powder bed-based technologies, and there you can deliver multifunctionality within single materials, such as things like lattices or metamaterial properties, but also even the parameter sets, right, can influence porosity. And those have relative functionality that can be deployed, and we can talk about that later. And then we've got kind of the extrusion technologies, and there's challenges there around how do you take into account this anisotropy, right? So the principle that materials respond differently depending on the action that the force is applied, because it's a layered-based system. So you're influencing kind of the production process, these inherent multifunctional properties. And that's where software, I think, and also intelligent design thinking and engineering really has to come together. And that complexity space when we're looking at multifunctionality can appear quite vast, but it's also an opportunity as well to be harnessed.
I can see that, but what are the key factors then that a design engineer might take into account, when designing a multifunctional part for him? What impact, can such parts have on quality, time, and even cost of the final part?
Absolutely. I think that those clear requirements from a business perspective are really essential. But then if we get down to kind of explicits, right, you've got max stress constraints, you'll have max temperature depending on your application that you have to handle. So these are key requirements that the initial materials you're looking at really have to fulfill at their bulk properties at the very least. So it's starting out with the right original materials, right? And then when you've got that material set that you know will at least fulfill the basic functions, how do you deploy these materials, right? Which technology are you going to use to put the materials in the right place and harness those properties within the regions of that custom part, right? And so there you might have a part with competing physics. One region might have thermal exposure, the other region might have mechanical, and there might be some kind of thermal stresses that emerge as well. Let's say, I don't know, like a battery pack for an electrical vehicle, right? That's a classic case. You want to get the heat out while keeping stiffness. So there you've got this consideration. How can you allocate the right properties of the material? Can polymers fit? Can composites fit? Could you think about a, say, for example, a thermally conductive metal, right, like an aluminium, complemented with a steel, for example, for strength, or titanium. So these are kinds of these considerations, but it's putting the right data and the right requirements into whatever optimization software you're using, like our own, for example, and that's where you would put in those prime material properties. So it's getting the right material data in first and understanding how you can't mix anything with everything, right? There are rules around what you can combine and not combine and what's possible. So I think working within those the reality of where multifunctionality can be deployed is really important. And that's then when you can run designs of experiments and then also production.
Okay, let's see if Elena agrees with you, all right? Because as a material expert, probably she has another point of view on the way she looks at additive manufacturing of functional part. Do you think, Elena, that such production necessarily involves a multi-material design, as Alexandra is trying to explain?
I mean, what we see is this multifunctionality can be improved or can be done by using different materials. But what we also see in the relevant industrial applications is that you can have, for instance, this multifunctionality in just one single material. No? So you need to consider also what you can make out of one material. And I allowed myself to bring an example directly from a space application. So we developed in front of IWS AM manufactured aerospike engine that I have with me today. It is one single material part. You can see it. You can find more information also in internet. And it's made of Inconel 718. But due to additive manufacturing, we could implement regenerative cooling, the cooling channels. We could implement propellant injection on the aerospike peak, let's say, and then using Inconel, apply high temperature properties to this engine application. And as you may know from conventional combustion chambers engines, there were concepts already a couple of years ago how to increase up to 30% effectivity of these engines. But it was not until additive manufacturing was there that let us print such a complex aerospike engine that we could really improve the effectivity. So I see there in just one material, improve cooling, these channels that can be used to preheat the combustion gas mixture, and then the high temperature properties. So this is just one example for one material. And then, as Alexander mentioned, obviously, if you move to multi-material, you can do graded structures. You can do composites. You could try in situ alloying and just modify by every element the composition of your alloy, layer by layer. For instance, get a brand new high entropy alloy or a brand new distribution of gradients. For instance, also to manage the thermal gradient in a turbine, in an engine. And then, so my answer to the question would be, we do have potential in the single material level and also in the multi-material level.
Yeah, and what you mentioned is a metallic part. And what brings me to this question, I've seen that metals are always mentioned as the ideal, material candidates when it comes to producing multifunctional parts. But can we not achieve such type of production with polymers or ceramics, for instance?
Yeah, sure. As I said in the introduction, we at IWS are mostly focused on metals, but you may be aware of some advancements also from other colleague institutes from IKTS who work on the field, quite strong on the field of ceramics, and they develop a multi-material jetting system where it's possible by using thermoplastic binder material or systems to print different ceramic parts, having this multi-material approach. They tried, for instance, in the past also to combine conductive, non-conductive behavior of different ceramics, to have a localized effect if you need a thermal conductivity or electrical conductivity on some parts. They also played with different kind of colors from ceramics or other properties. So this system is out there already, and you can use up to 4 different microdosing systems to have 4 different materials.
Okay.
And also on the field of polymers, fuse deposition modeling, it is also state of the art to have different filaments and have multi-material approach to have, for instance, gradient on hardness of your polymer parts. Using elastomers, for instance, Serion has also different machines there to combine steel and ceramics, for instance, zirconium oxide. So I think the state of the art is showing us that multi-material is a big deal for all different kind of materials, not only for metals.
Okay, Alexander, and you have mentioned laser-based power-based laser technology as one of the additive manufacturing technologies that can be used to produce such parts. What other additive manufacturing technologies do you see as potential production candidates for such productions? And my question is really to both of you.
Yeah, like asking what's your favorite child. So I think kind of one technology type that's really interesting, I think, is cold spray, where it's incredibly productive, and because of the mechanical technique that's being used to deposit the material, you can avoid some issues, say, for example, like into metallics and so on that need to be handled. I do think that laser powder bed fusion is interesting, right? And I just want to, if I may come back to an interesting application with lattices as well, with metal structure, single materials, where we've seen some interesting work that we've been involved in within kind of heat exchanging sort of fluids, where there's this like competitive analysis between thermal expansion on one side versus conductivity, and you have this trade-off, right, with the dense kind of lattice versus the sparse lattice, where one is good for the other, and where do you allocate the best one, right? Which I think is really interesting, Elena, also with your part. I do think that some of the more traditional technologies, I mean, you mentioned FDM, right, and polymers do things, have this kind of latent capability that maybe is just starting to become adopted. But I think specifically with continuous carbon fiber and chopped fiber production, where you have really strong capability, right? So you can really produce specific strengths that is like, you know, black metal, as they say. And there one can think about, say, combining frequency dampening, say, materials, such as your TPUs and so on, in areas to avoid, say, frequency issues, while at the same time applying the directionality of those fibers to best harness that particular stress distribution within a part. The question comes down to how do you allocate that, and we're working on that as well within our projects. And I'm sure there's a whole host of different manufacturing technologies. I think ceramics is an amazing potential as well, especially with the freedom, material freedom that can evoke.
Yeah, Elena, any other examples of technologies?
Yeah, I absolutely agree with Alexander. You cannot really pick up one technology, because as I mentioned, what I showed you before, this engine, aerospike engine, is an LPBF part, so you have the complexity from the powder bed.
All right.
But you can, I'm especially personally a big fan of laser metal deposition for multi-material approaches. I just brought also another part, probably you see the different colors, bronze and steel, where you can really do this very well-defined, let's say, gradients. No? You have the nozzle technology, you have different powder feeders, and you can skip, for instance, by multi-material approach, the recycling problems that maybe with the powder bed fusion, combining different materials are there. So you have sometimes the design complexity, you have sometimes the material flexibility. I think every technology has potential to develop or to become a big player in the field of multifunctional AM, from my point of view.
But Elena, in the context of multi-material manufacturing, what do you think the geometric or structural challenges that need to be met at the design level are?
Yeah, sure. As you all know, every technology has its limits concerning geometry. For instance, if you want to move to print such an engine with the nozzle technology, with LND, you would be able maybe to have a smart thermal gradient included, but you cannot print the cooling channels or the, let's say, propellant injection channels. So you have design constraints on the nozzle technologies, definitely. You can scale up, but you cannot go just, let's say, in infinite complex with these technologies. On the other side, with the powder bed technologies, it is quite a mess still, and even though there are solutions out there, also I think Alexander will tell something about that later on, but also from Fraunhofer. There are solutions to work on powder bed with multi-material, but still it is not a technology that is completely accepted in industry, because there are still some limitations with the recycling of the material, with maybe contamination within your chamber, oxidation, whatever, no? And also long-term effects of combining different materials, sedimentation and so on. So we need to, let's say, you need to pick up a technology when you have a design in mind, and then see which are your limitations. Is it scaling up? Is it thermophysical properties of two different materials maybe? Is it design restrictions? But in every technology you would find something you need to develop the other one.
Yeah. I can see that we already have some questions from the audience, but I would like, them to wait a little bit before we answer them. Maybe, Alexander, can you, provide or explain if we can provide multiphysics capabilities to the part at the design level?
Absolutely, and I think Yeah, sure. So I think multiphysics optimization or drivers is a key enabler, right? And I think it's beyond just like a naive view of saying, well, this region's hot, so let's put a conductive material there, for example. It's looking at all of the different overlays, and that's something that, of course, our software is incredibly strong at, around handling different physics and weighting those specifically for particular requirements. And I mean, that's something as well that, looking at it from an optimization perspective, coming at it depending on where you are in that decision tree, whether you're coming at it from the design or you're at the manufacturing step, how do you handle certification? Do you see what I mean? And you need to have these really clear, explicit tests in how you deploy multiphysics. But definitely, and I think that's something that is emergent, and around especially the simultaneous when you're bringing things like topology as well as material properties, individually as a fixed volume that you're looking at material properties within that, or you have other design freedom as well. That's when you have the ability to, per iteration, within the kind of work that we're doing, to allocate different material properties within topology relationships. And as with everything, it's bringing in those machine constraints. And I think you spoke very eloquently about that, but also that after you've got something off the print bed, that's not the end of the story, right? There will very likely be finishing. There may be heat treatments. There may be post-CNC machining. There may be an assembly that particular part's going to go into that has other functions. And I feel it's quite relevant to think about that whole process, right? And say, can you make a compromise at one point in your chain that solves problems later down? Or if you can consolidate and kind of bring upstream into more of the additive process, some of the issues that are maybe being resolved later down that might be out of scope. And I think this probably brings in the concept of digital thread, right? And kind of true digital twin through that step, where looking at multifunctional parts, in a sense, is also looking at how your maybe existing silos are within that workflow of product development to manufacture. So there are, gives and takes. And Elena also brought up, I think, something quite important around sustainability, right? If you are looking at different materials that might have a different sustainability question, then whether you're looking at a single material and allocating functions through that. And then you have this other kind of, sustainability isn't just a recycling question, it's what does your life cycle look like for that part? If you can reduce, say, weight on a vehicle that's incredibly fuel consumptive, say in aerospace, right? Or transport, with a multi-material part, for example, that might save embedded carbon much, much more than using a single material part. But in many cases, it might not. So this is where kind of, it's not a black and white decision. There's really a series of gray that you've got to look at and think, okay, if I take this choice, here's my result. If I take this other choice, here's my other result. And that's from freedom that really also repeatable workflows are really important, like say the ones that we're also developing.
Yeah, but this is still a little bit unclear, because how can one reduce the risk of product failure and obtain a final part that is as close as possible, to the simulation that the design engineers performed, or prior to the printing process?
As with all additive manufacturing, you don't just look at the bulk material properties and hope for the best. It's about understanding a specific machine with a specific material from a specific provider, and you're applying specific parameter sets to that, and a consistent post-process. And then you have to control that chain, and the material handling through that workflow has to have been done correctly, because moisture coming in will have influences. So looking at kind of ensuring that your parts are as you would wish is more than just an additive process. It's thinking, okay, that whole chain has to be handled correctly. And I think when we think about multifunctional, we might also think about dynamic control and these kinds of concepts. But I think with everything, it's around locking what works and using that and deploying that, and not having to bring everything in all in one go, because otherwise it's impossible to implement. And I think that practicality of what are the small steps that organizations can take and businesses can take to be maybe a bit more multifunctional and achieve, say, some cost savings or sustainability benefits or performance increases, rather than having to go right at the end to kind of very, very exotic multi-material components, which might be in the future relevant, but right now, could we do things in single material adjusting properties strategically?
Yeah. Do you have any specific illustrations that might show the right steps for the engineers to take? And for Elena, that will be to see if she has any example that might illustrate, or the right manufacturing processes regarding such type of production.
Sure. As mentioned, we have this development with the aerospike engine. I mean, it might see or look like an easy approach, but we started with this in the year 2016, actually. And the fabrication of this kind of aerospike nozzles was available until then. So the usual combustion chamber used conventionally is based off a level nose and a normal combustion chamber, and this aerospike and annular combustion chamber are quite new due to this AM specific design. So we moved from the, let's say, geometrical demonstrator in 2016 up to 2020 with the hot gas testing and the real let's say, situation or real condition for a space application. So this has been used with the thought of moving a satellite with this kind of engine. So we moved to this hot gas testing, and we could successfully see that from the geometrical demonstrator, we moved to a functional demonstrator. So you always need to take into consideration one thing is design of multifunction, and then until you prove the testing, some years might be there in between. This is one example. I have another example also in the level of space. I hope you can see it. This is an antenna, a 3D printing antenna with topology optimized structures, as you might see. It's made of titanium 6.4, also for a space application project with the European Space Agency. And in this case, again, a multifunctionality. We have an antenna functionality and a lightweight design together with this previously mentioned functionality. So we have designed these different structures here and simulated, as Alexander also mentioned, to come out with results made of titanium 6.4 that even improve further on the weight to be set up in space. And I mean, this is just a smaller demonstrator than the antenna in the real application, but you can really skip up to 30% of the weight by doing like this. So just two examples coming out of different industrial relevant projects at Fraunhofer.
Thank you, Elena. Thank you. Alexander, do you have some software tips that you would like to to share?
Of course, yeah, I can show something. I'll show something in a bit, maybe at the end of the discussion, just to kind of show what we're doing. But I think also just in terms of practical examples, I think it's quite a good timing, this webinar. Recently, you might have seen NASA approve this cold spray technology for multi-material within propulsion. So they're applying conductive thermally and also strength-based materials. I think that was very powerful. But I love the radio antenna because I think there's a lot of challenges when we're thinking about, say, coefficient of thermal expansion within radio frequency, and how do we handle that? And I feel multi-property is interesting work being developed there as well. If I may kind of also take a bit of a polymer angle too, so we're being friendly to all the different material systems out there. There's a number of technologies also that are able to kind of align fiber directions, right? And fibrous directions can have not just mechanical implications, but also frequency implications, conductivity implications as well. And there's some very interesting work now with, I think, 3 to 4 really interesting technologies coming out that we'll know about that allow demonstrated alignment of these fibers in automotive, specifically around weight savings. I think we did a project with alignment that we kind of cut the weight by over half, cost by over 50%, and went actually to a single material from a previous multi-material. It used to be a bipolymer metal part within automotive. That was very interesting.
Okay, so we are going to pause a little bit to take some of the questions from the audience. And the first one is one from Bram. How do you see the practical use of multimaterial printing in the future? Will this be limited to materials in the same family, say metal, or do you see combinations of, say, ceramic and metals? And I think that's one is for Elena.
Sure, I can first give my opinion. So I see, so our opinion is, let's say, the multi-material approach is still focusing on basic research, or let's say research applications. We do know, obviously, that there are some concerns concerning maybe recycling of the parts. Also the long-term effects of having materials with different thermophysical properties, how stable this material combination is in the long term. This is obviously something that needs to be studied for longer periods. Then concerning recycling, the circular economy, how to deal with the lifetime of a part and how to recycle maybe the materials involved there. But definitely, I do see applications. So there are already applications with these graded structures in the engine level. For instance, we have different projects with the company Rolls-Royce where they have graded structures already flying, let's say, in their engines. And I think there is much more to come because it's still, the whole is still a little bit more focused on research, but there are already material combinations that work properly and are being tested right now and be ready for industry. And then what I think concerning combination of materials, I do definitely see the combination of different material families, ceramics and metal. I mentioned some applications maybe where you could have the conductivity of a metal, but also the non-conductivity properties of a ceramic there. Also for medical applications, we do have projects where we work with the aesthetic printing of brackets that combine polymer and clamping structures made of metal, of steel, 316 for instance. We do also have the combination of metal and ceramic also for dental applications. So I think there are no limits as long as obviously the material properties and the material science is well understood behind the real part.
Okay, I see. Thank you, Elena. Bram, I hope this answers your questions. We are moving to the next questions, which is one from Denise. And he's asking, how do you manage quality control on multifunctional parts? So that's his first question. He has another one that is coming. How do you manage quality control on multifunctional parts?
Yes, I think quality control is really important. And this is where I think that concept of digital thread is essential around your metrology approach, around your material handling, and also I think there's technology now that we have that we can take volumetric inspection as well of these parts, and then look at how we compare that against our desired material properties also within the volume. And it's every part of that workflow needs to be actively engaged. And I think any simple step, a simple mistake, unfortunately, can create failure, right? And unknowns. And that's a risk with additive manufacturing, where because of the consolidation of all of workflows coming together, that if we aren't really precise about that and really investing in that, then it's hard to achieve.
Okay. The next one is still from Denise. What is the limiting factor to design multifunctional parts for AM at this moment? I think that that's for you, Alexander.
Thank you. So I think from the design side, every design decision is also depending on what's possible within the machine, technology, and the material combinations. And there's a lot of work still to be done in general from an industry perspective around material properties and how are material properties changing, how are material properties responding, not just initially, but also over time, right, with fatigue, with other considerations like that. And so I would say the constraint actually comes down a lot to still quite a lot of initial upfront investing that has to happen around understanding those material properties and how they're behaving. So you're putting the right material data into the software, right, in order to then allocate. Like sort of our technology is able to allocate different materials, different multifunctional capabilities, process parameters within it, and then also send out things to be produced. So it's also based around what's coming in at the input and what's coming on the output. And that's really, really essential.
Okay. The next question is from Wayne. Is using copper shape memory alloys for heat sinks or heat exchangers with shape change with transit fluid thermal conditions practical? I think that's a question for Elena. Elena, do you understand the question? Because
yeah, I think so. Concerning copper, the printing of copper in general, there has been, this is a quite hot topic right now. There's a lot of movement in that direction. And we know from different projects that it's feasible also to integrate different functionalities on a copper parts. We move for laser powder bed fusion and laser metal deposition to green and blue lasers, not working with infrared lasers for copper because the absorption properties are not really the appropriate ones. And have already done in the past conventional heat exchangers made of copper. Obviously, the use of shape memory properties on copper needs to be studied as far as I know, because I mean, it's fancy to include this property, but you need to also observe on the long term if this shape memory property is really stable and can be applied for an AM part. So we had enough problems in the past to get a very good absorption of copper to process it. And also one restriction that we have at the moment to work with heat exchangers is the chamber size. So we do have conventional machines out there, for instance, from Trumpf, where you can print up to 100 millimeters parts. I think Trumpf is also working on a scale up of that machine, but we are still limited. So yeah, heat exchangers are feasible, but with some restrictions. No? So it's practical, but let's say we still need, after we have control or all parameters on copper printing, and more research on that for bigger parts, for instance.
Yeah. So Wayne, I hope this answers your questions, and Denise, I hope Alexandra's response to your questions very well earlier. Or if not, please share your feedback in the Q&A again. The next one is the next question is a question from Kevin, and he says, "Hello, Alexander. From my understanding, multimaterializative manufacturing refers to printing of a body part in a single job comprising of different materials fused together into a final product, without the use of adhesives as a bonding assembly. as a bonding assembly method between the two different materials or parts for applications such as titanium and carbon fiber reinforced polymer joints. How do we ensure the bonds between the materials in a final multi-material additive manufacture product are well bonded? How do
What
we
a
ensure
fantastic question, Kevin. Thank you. So I think this relates also to kind of how does the interface between material properties behave? And it applies not just to multi-materials, but also within metamaterials, right? Or parameter sets. Within our software, we have this overlap capability and can treat the interface of these material properties separately, if those material properties are known, or we can put in assumed values, so there's that. But then also with respect to the manufacturing process, how do we ensure that they're actually bonded correctly? And as Elena said, it's around what is that material system, what is that process? So I kind of mentioned the cold spray technology previously, that because it's mechanically being bonded, there's really nice adherence, and there's been studies showed that actually the material properties transition from one to the other consistently. But even if we're looking at changing a process parameter A that's say slow and giving you a dense porosity versus a process parameter B that's fast and giving you more of a lighter porosity, there, even in that interface, one can create some risks for crack propagation. And so that's where it's not just what we can simulate and what we can predict, it's how we're handling that test process and feeding that data back in a loop that can then allow us to improve over time. So partly it's iteration, but how do we minimize that iteration? And that's with the right digital approach.
Okay, Kevin, hope this answers your questions. If not, please note that Alexander likes to be challenged. So come again.
Thank you.
if it didn't answer your questions very well. So the next question is one from Lopez. How important is simulated computer models, and how far have we come in this field for multifunctional parts?
Is that meaning I've got to do a demo now, Katie?
Yeah. Yeah.
Okay, what I'll do is I'll just do a quick screen share. How about that?
Yeah.
And I haven't used this webinar platform before, so please exclude any rough edges.
Okay.
So you can see my screen, right, guys?
Not yet.
Let me know when.
Okay. Okay. So I would like to advise the audience to enlarge their screen to be able to see what Alexander is going to show. And location, this is probably for you to respond perfectly to your question.
Okay, hopefully others too. So here's a caliper that we've got here, brake caliper, which is interesting because you have kind of mechanical and thermal conditions, right? So here we've loaded some boundary conditions, mechanical, we've got our thermal here. We can also take into account the coupled thermomechanical. Here we have our multi-objective editor. So this is where we're able to take in boundary conditions on the left and feed them through extracting data to create what we call multi-objective workflows with different physics. So here what we have now is 3 physics, mechanical, thermal, frequency. We're able to also take in this thermal equation and connect it to the mechanical to also look at that coupled thermomechanical. So that's really quite powerful. And it's more important also to think about what are we going to do around multiple objectives and constraints. So we're able to take in additional constraints as well and limit, say, based on costs. So it's not just the physics, and run that through. And so what we've done here, we've created a weighted series of experiments, preferentially looking at either those thermal or mechanical considerations. In this case, we're looking at a steel and a copper here, and we're saying it's a discrete allocation instead of a gradient allocation. Now, here's something that's pre-computed, right? So we've got a series of results that are changing depending on the particular weight of the optimization, right? So we've got this particular part, and you can see how those material distributions have been changed based on how much we're prioritizing the mechanical properties of this part, right? And so here you can see the different physics that we have looked at. So here we have the thermal properties, the different material distributions, the displacements that are predicted as well. And we can kind of jump in here and dive to see distributions both against each of the physics that we've looked at, say your frequency or thermostresses, and also then kind of isolate exactly where you might be wanting to look at. And further, we've got kind of I don't know, these comparative features, so you can kind of look at your axes and decide how you are going to kind of trade off against, say, stress versus displacement versus mass, for example, before going on to manufacture. So I would say kind of the simulation and optimization side has really come a long way, right? And I'm slightly biased, of course, in this regard. Really, it comes down to kind of what are your material properties, how are you allocating that? Are you looking at kind of fully anisotropic matrices? Are you looking at how these relationships are being pulled together before you go on and export it? And we can talk about exports later, but depending on multiple meshes or different volumetric data as well that we can use.
I see. So, Lopez, what do you think about this answer? The next question is one from Kamal. SpaceX claimed to use 100% additives manufacturing technologies. How to prove this, and is it a sign that the technologies are mature? That's a question for both of you. Elena, would you like to go ahead for this one?
Yeah, I would like to comment. I'm surprised about this this information. From my point of view, I cannot really imagine that they use 100% additive manufacturing for their technology. But what it's definitely, I mean, how to prove is, yeah, we are not going to check every part there, but what it's definitely fact is that we do have an incredible boost over aerospace and space applications in the field of additive manufacturing. So, and the aerospace industry is a pioneer from my point of view in the use of additive in general. We do have enough examples, as mentioned, Rolls-Royce, Airbus, European Space Agency, NASA, and so on, putting parts up there in space and aerospace made by additive manufacturing. So they increase, from my point of view, a lot the confidence on these parts for users in general. And we see that other branches are just following this trend, like automotive, like medical, and so on. So I wouldn't say the technology is mature to make 100% of parts in space or aerospace, but I would say that we managed to show quite a lot of examples in the past couple of years that it's possible and it's reliable to use additive for parts that make sense from the design point of view, from the functional point of view, from the cost or lightweight point of view. So I think a conventional is not going to be substituted in 100%, but it's going to be a cohabitat between conventional and additive.
Oh, I don't know if Alex wants to comment on that, on Spacesuit.
Yeah, so I also, I don't know specifically about that particular percentage. I know that they do use additive, but I'm not sure that it's 100%. But I think kind of Relativity Space maybe is one organization that is predominantly using a lot of additive, and they've, as I understand it, have developed a kind of blown powder welding kind of technology specifically for rockets, which I see they've recently raised quite a nice healthy round around recently. So congratulations to them. So I think that's a signal, also together with the NASA recent kind of work around multi-material, that these are now being used. But I would also say kind of multi-property has been around within single materials also for such a long time. And if we're looking at kind of overmolding within polymers or kind of different bimetal casting technologies, some of these things also have been prevalent and also used. And I'm looking forward to the coming few months where also more on the multi-material side of things, we know that there's some interesting results that are going to come into light, but I'm holding back saying right now.
All right, no problem. So the next question is Denise again. I'm really happy because our audience is very engaging today. So how does the cost influence the design in the software?
So within our particular software, we can build relationships between, say, for example, printing parameters, and production speed, which will have an effect on cost. And then you can get a trade-off, for example, between how fast you want to produce something and where you might like to trade off against your denser or less dense materials. So we did some work with heat exchangers, for example, allocating the dense material properties where the most thermal demand was inherently, and also changing that geometry. But the other side of it, of course, is you need to have a view of that, ideally, that full manufacturing cost. So it's not just what your process cost is, there might also be post-processing costs. And so those modules can be built in quite readily as well and taken into account. And I can't help but also kind of extend it also into these non-engineering relationships, such as also sustainability and life cycle impact. These are things that we need to consider. And I think this is where this kind of multi-objective software can really come into its own. So you can not just kind of make your engineering department happy, you can make the business side of it happy as well. And also we should all be environmentalists these days, I hope, and also the environmentalists happy.
Okay, Denise, I hope this answers your questions. The next one is probably a question for Elena. And that question is from Wayne. Is it possible to print plastic insulators and conductive metals in one go? The potential applications can be in the field of electrical coils, etc.
Actually, it's a matter of fact what you define one go. I mean, I think it's possible to print these insulators and conductive metals with one technology. For instance, dispense printing or fuse deposition modeling and so on. But obviously, you need the different materials, you need the different cartridge if you work with dispensing. So it's not, for me, one go is just probably just with one feeder. You need different feeders, or you need different filaments, but it's feasible with one technology, at least. Yes, so then I would say yes to this question. But obviously, you need to consider, switching between material feeders, maybe cleaning in between, or having a buffer layer. It depends to guarantee for a chemical understanding between the two different materials. So it's maybe not so easy as it looks like. You need to let's say understand what's the material science behind. But we can print insulators and conductive metals with one technology.
Yeah, thank you, Elena. Wayne, I hope this answers your questions. And Lokesh is coming back. I think that he has understood that you like to be challenged, Alexander.
Thank you, Katie.
And
thanks, Lokesh, too.
How close is it to the actual physical model?
So it, of course, depends on the material properties that are coming in, right? And how well controlled that machining process is. But we've had some quite good correlations in the work that we've done. And as with everything, when you are experimenting, then you have an initial kind of first go with optimizations using the understanding that you have. Maybe you've achieved your material properties from a homogenization approach or other micro-mechanical approach. And then you're putting these kinds of, within a degree of margin of error, material properties into a system like ours, doing a series of designs of experiments, if it's a multi-material or a multi-parameter or different lattice technology. And then one might go through a series of kind of efficient testing, right? If this is a new approach that you're doing, take that test data back in, and then we would maybe run another cycle. So that's kind of a workflow that in a very, from an early stage of R&D that one might do. However, if, say, for example, some of our clients are really clued up in how a parameter set might influence a particular material property, because they have their certified parameter sets, right? That they know by following the specific chain of material type, process, through to machine, through to specific post-process, here's my material properties. And there, with that deep empirical understanding, you can really leverage the most from your simulation and your optimization.
Yeah, correct. Elena, before we move to the concluding thoughts, I've recently read that a consortium of companies will develop novel active materials that may enable the production of multifunctional parts. Could you please a little bit explain how it could be possible to achieve?
I'm not sure, Katie, if I got your question right. You mean how to collaborate with different companies to get such?
No, I'm just raising your attention, on the use of potential novel active materials, to produce multifunctional parts. So any idea or any explanation to provide regarding such type of development?
Yeah. So for us, a novel material made by additive manufacturing could be already in situ alloying using laser metal deposition, for instance, where you can tune the elemental composition of your alloy in such a way that was not feasible before. So for us, this is a novel material. Also a combination of hybrid technologies to get a certain multifunction is for us already the kind of novel approach to print materials, composites, and so on. High entropy alloys are also a hot topic at the moment, where we can get the combination of different 5 elementary materials to get, for instance, high wear resistance, high mechanical properties of parts that were not there before. So the problem over there is not the novel material, but to find the proper application maybe for this new alloying that it's been feasible by using additive manufacturing, for instance.
Okay, thank you. I think that we have one last question from Denise. How is the now I'm not seeing the question anymore.
I think he pulled it back, saying at the time. I did read it, so I can. Maybe I can give it a good shot. I think it was something to the lines of, does it take into account post-process material properties within the part? I think this is an interesting topic as well, in terms of how do you progress from your design material modeling to your process modeling and take into account that full thread. And that's something that we're working on to pull into account, say, in-process stresses being embodied as well. But I would always, look at, from the point of view of practicality, using the material properties that are post all of your post-processing. So what is the material property of the full chain of that material? So not the bulk, but after it's been heat treated and CNC machined and whatever else you might be doing to it, and use those material properties. And then, of course, one can take that in. There are some stochastic approaches we're taking, some data-driven modeling around those kinds of themes that will be coming to light shortly.
Okay, thanks. Thanks, Alexander. I'm going to ask your concluding thoughts. So speaking of software and material solutions offered to date in the additive manufacturing industry, according to you, what are the main areas for improvement that should be considered to take the production of multifunctional parts with additive manufacturing technologies to the next level? So any final thoughts regarding this topic as we are moving to the end of our conversation, unfortunately for me?
Elena, do you want to start?
Sure, thank you. So, as mentioned at other parts, I think circular economy is a topic that is in every discussion right now. Yeah. So we need to consider if we maybe include different functionalities, and we expect the part to have an end, a lifetime end. How to recycle all of these different functionalities, all of these different materials. Again, the same for multi-material approaches. Just to think forward at the end of the lifetime of that part. This is one aspect. Then, for instance, for us as material researchers, it is a hot topic for us how to control, let's say, with powder mass flow sensors and other sensors to control exactly, if you move to a multi-material approach, these graded structures. It could be very nice also to control it really maybe on the sublayer approach and do have a tune modification of the material properties. And upscaling is also a hot topic. We have seen for the complex structures, we still have limitations in the powder bed approaches. It would be nice also to see in the future some upscaling for bigger parts, for large parts, additive manufacturing, again, for mobility or for space. And long-term testing is also a huge topic. Is the part so effective after 5 years, 10 years? Under working conditions and so on. I think we don't have enough information right now to answer this question. It would be interesting for me also to know.
Thank you, Elena. What about you, Alexander? What's happening on the software side of the business?
So I really see there's a lot of work and opportunity to be done around this connectivity, right? I've mentioned it a few times, from instrumentation of process, from how are you handling your material, managing that material, and each step, if we're taking a material-centric approach to things, which I think we're doing quite well, is each step has influenced, almost like adding a filter onto the material each time you're adding a process. And it's understanding how all of these influences happen, and then having this kind of data log, as Elena also mentioned, that will confirm whether what was allocated, optimized, simulated, applied, and decided on actually has been achieved. And if it has or has not, that's actually an opportunity to improve either manual processes or even the physical processes of manufacturing themselves. And it's this integrated loop and connected loop. So that's what we're working on quite actively.
Correct. Thank you very much. Thank you, Alexandra. Thank you, Elena, for joining us for this panel.
Pleasure.
So multifunctional part, built with additive manufacturing. I would also like to thank the audience. You guys were very, very engaging today, and I hope this panel has been useful in any way to you. I'm going to close the panel now, since we are reaching the end of this nice conversation, and I would like to, invite you to stay tuned for the next panel, which is coming next month. Thank you very much for your
Pleasure.
time, taking the time.
Thank you.
Have a nice day wherever you are in the world. Bye.
Bye-bye.